So hello and welcome to our third workshop in this series. So today we're going to be looking at programmatic search and analysis using the CSD Python API. We will be recording this session, so if you'd prefer not to be on camera, please turn your camera off now. So some more housekeeping before we start. So as I mentioned, we will be recording, but we will turn the recording off during the hands-on part, so you can ask us lots of questions during that part. So if you could mute yourselves during the demo and this presentation, that would be appreciated. If you do have questions during the presentation or demo, then you can type these into the chat box and we'll try and answer as many as possible. Just so we remind ourselves where the chat box is and how to access the chat box, then now's the time to open it up. So you should see a little speech bubble at the top, and tell us where you're joining from today, and a very British question, what the weather is like where you're joining from today. So I'll give you a few seconds to tell us more about where you're coming from today and what the weather is like. While you're doing that, just a reminder for the hands-on part, you will need Mercury. You will need the Python API installed in an active CSD Core or CSD Enterprise license, and you'll also need the workshop handout. You should have received more information in the email that we sent you earlier this week, and we'll also type the address of where to go to find more information in the chat box. And another reminder, this workshop is designed for users already familiar with Python, but beginners to the CSD Python API. So I can see that people in the UK, Ireland, warm and sunny weather, cloudy in London. Nice. Brazil looks nice and sunny. I'm looking forward to seeing more of your weather in the chat box. Okay, so for the next 90 minutes, we'll be giving you a short introduction and overview before showing you the API in action in a demo. After that, you'll have the opportunity to try some guided examples for yourself, and we'll finish by showcasing more advanced functionality before testing you on your newly gained knowledge in a fun quiz. So after the session, you should be familiar with how CSD entries are represented in the CSD Python API. You'll know how to access CSD entries, read file formats, run a search, and output your results. Oops. So before we go into the main session, we wanted to introduce you to us, your hosts for today. So joining me today are my colleagues, Alex, Natalie, Ilaria, Yinka, Andy and Eva, and they'll be on hand to help during this session. So now you've met us and you've told us what the weather is like where you're joining from, let's find out a bit more about you. So you should start to see our first poll of the session, and we want to know whether you've done any of the following before. So it should just be popping up on your screens, either on your screen or on the right-hand side. It should be the first poll. So have you attended a CCDC Virtual Workshop, used Python, used the CSD Python API, searched the CSD with Conquest or WebCSD, analyzed structures with Mercury, or none of the above? So I can see some responses coming in. So it looks like a lot of you have used Conquest or WebCSD before. Some of you have used our Python API before, and some of you have attended a virtual workshop. So that's looking good. I'll give you a few more seconds to reply. So before we explore and analyze structures in the CSD, just a quick reminder of what's inside the database. So the CSD was established in 1965. It contains over 1.1 million structures and every organic or metal organic crystal structure, including structures associated with ASAP articles, patents, repositories, thesis publications, or published directly through the database as a CSD communication. It really is a community effort with structures determined by crystallographers worldwide, and every single entry is enriched and annotated by experts at the CCDC. So that's really to aid the discoverability of data and knowledge from the resource. And you can see on our slide the growth of the CSD since 1972, and one of the structures in the CSD which we call kitten. And if you've attended some of the workshops before, you'll hopefully all remember what kitten is. So as well as being a cute cat, it's a CSD ref code, which is our database reference code. And these contain 6 to 8 characters, and they're used to identify entries in the CSD. So just a reminder, structures of the same substance are assigned the same 6-letter code with an additional 2 numbers and are collected together in what we call a ref code family. And so we class same substances as things like polymorphs of the same substance, new determinations or re-refinements of the same substance, or determinations at different temperatures, pressures, etc. Along the way, we are going to be seeing some ref codes, and you'll see that some ref codes sound more familiar than others. So for today, we've looked at butter and rocky, but actually there are quite a few with ref codes that feature API in the name. So we're hoping after today, you'll be an API gem rather than API bad. So as I mentioned, the CSD contains a mix of organic and metal organic structures. It's used in a variety of industries and in academia, and it can be used for both education and research. As well as standard crystallographic information, it includes additional data on polymorphic families, melting points, crystal shapes and colours, and oxidation states. And it also includes links out to other data repositories. There's a lot you can learn from looking inside the CSD, and you can start to see trends emerging over the decades. For example, if we look at the change in chemistry, we can start to see the emergence of metal organic frameworks, which now account for about 10% of the database. Looking for trends is made much easier by using the CSD Python API, and we now use it routinely at CCDC, so we can discover things like which elements are most prevalent in the CSD. And we also use it to see who's top of the charts in our conference leaderboards. So if you've met us at conferences, you've probably been involved in one of our leaderboards. We can also use it to see who has got the most structures in the CSD. And so you saw a race on the top right of who's the most prolific author. And we can see that as of 2019, it was Arnie Reingold. So with a little Python knowledge, you could create your very own race and with your research group or in your institution. So to help you get started today, we'll be guiding you through how to make graphs like the one that you can see here. And this will be in the try one part of today's session. So before we get to know Python, 2 more questions to help us to get to know you a bit better. So if you could tell us which operating system you're using and what you're interested in doing with the CSD Python API. So you should see those polls again on your MS Teams screen. So I'll give you a few seconds to do that. So what operating system are you using? And then what are you interested in using the CSD Python API to do? So, a lot of data mining, structural analysis. If you have said other and you want to add any more details to the chat box, please feel free to do so. So our CSD portfolio helps you search, visualize, analyze, and generate new insights from the CSD. And today we're going to be using the CSD Python API in our CSD core suite of software. So with that, I am going to hand over to Alex, who's going to be telling us more about the API.
Thank you very much for that. So I'll be giving you a very quick overview about the API, what it is, and why you'd want to use it. So API in this case stands for Application Programming Interface, not the pharmaceutical type of API. And it essentially allows you to interact with our CSD tools without having to worry about using a graphical interface. And there's obvious benefits to doing that. Mostly because you can make your own workflow, you can make your own analyses, they're tailored to your needs, but you can still interface with Mercury and Hermes through the GUI if you wish to run some of the scripts. Try and get this to work. There we go. So why Python in particular, and why for the CSD? Well, the CSD, as you've just been told, contains millions of structures, and it's the idea that you can run consistent analyses across these structures, and you can create tools that can be reused repeatedly. And because it's in Python, you have access to all the other libraries that Python comes with, such as SciPy, Matplotlib, NumPy, and many, many more. So if you've never done scripting before, which I should hope you have, this is a Python talk after all, what having scripts allows you to do is just automate the whole process. You can create reports, you can look at some type of analysis you couldn't do visually very easily, and it makes your data, it makes your results consistent and predictable. And further to that, you can share your work with other people so that they can replicate your work as well. And it allows for sort of building up of tools very easily. Now, the API itself is just an interface. So it stands between your scripts and our library. And it creates a link between the two in the way that you can go back to the library and sort of, it's dynamic, so you can interact backwards and forwards. You don't have to worry just about sort of sending data and then receiving it back, and then that's the end of it. And that's really important. And so the most important part of any library is the documentation, because this is where you find out all the information about how the tools work, how to access particular properties, and it's really the starting point that I'd advise you all to start from. So there's a couple of ways you can access it. So in Mercury or Hermes, you can use the drop-down menu, and inside of it you have the documentation label there, or you can go to the website, and this is where you'll see at the top. The documentation has a search function, which is hands down the most useful thing you'll have there. But as well as that, it has very good descriptive documentation. So these are not just about kind of what data type you need and what kind of inputs and outputs you need to your functions, but also what do they mean? Like what's this variable? Like where does it come from, and how would I use it? So I'd recommend to everyone to have this open at some point as you're working through the handout. Now, the other part that I've mentioned is that you can interface with our software, with the GUI, so Mercury and Hermes, and this can be done through the Python API menu. And what it essentially allows you to do is it allows you to access your scripts that you've written, or the ones that we've built in, and allows you to run them on the structures that you have loaded up in Mercury, for example. So you don't have to worry about using command line and running your analysis through that. So it's very user-friendly in that sense. Now, the part that I want to focus on quite heavily today is the overall structure of the API. Now, I'm not going to go into high detail about each class and sort of how you'd find things exactly, because that's what the documentation is there for. And I'm trying to make as clear of a picture as possible as to how things are laid out so you can go exploring yourself. But the most important part is the structures. So how do we handle structures? We have two approaches, is reading and writing. So that's CIF files, that's entries within the CSD, and how do you get to them? And the other part is searching. So this you don't necessarily know what structure you want, but you know what kind of thing you're looking for. So if you're looking for a structure for aspirin, you have the search function that handles the structure handling. The next level down is the data analysis. So this is essentially how do we carry out analysis of the geometrical structure or the interactions that occur within the crystal, or other descriptors that you might be interested in. And this really forms the foundation for a lot of our tools. because it's from this that we can start creating sort of understanding of what's in the CSD and what we can learn from it. And then below that, again, we have specialist tools. So these are things that utilize the data analysis layer. And so pharmacophore and cavity, docking, morphology, powder patterns, hydrogen propensity, these are all, there's many, many more, and I invite you to check out the documentation for them. But these are to be used by people who are specifically looking for them. And so what we're going to be focusing on is predominantly these two. And in the handout, you're going to be doing some of the geometry analysis as well. So I hope you're excited for that, because you get a pretty graph at the end of it. So just to kind of give you some orientation as to what you'd be expecting in the structure handling part of it. So in the reading and writing, so that's the IO, there's three main classes that we use. Those are entries, crystal, and molecule. Now, the entry class contains things that you would find as a submitted entry to the CSD, if you like. So general details, authors, DOIs, metadata about the experiment, what color the crystal was, what kind of solvent we used, so on and so forth. Whereas the crystal object won't contain the journal information, but it will contain the crystallographic information. And that's stuff like symmetry operators and is the system organic? Like, what's the molecular? Like, everything is within this sort of crystal object. And then the molecule contains the molecular data for that, which contains, furthermore, the atoms, which are the bit that a lot of us are interested in, of course. Now, the atoms, they have a massive list of properties, the most basics being coordinate systems, what kind of labeling you have, charges, occupancy, so on and so forth. Honestly, the list is very long, and I invite you to go through the documentation to find out everything. What's important to know here is that you can go from an entry into a molecule, and you can get the crystal from an entry as well. So you can go up and down if you wish. So if you want to create an entry class, you can from a crystal. But there is a read and a write function within our API that allows you to either read or write an entry, a crystal, or a molecule, and I'll be demonstrating that through the demo. So that's just the overall input and output. Now, in terms of the searches, what we have four main types of searches that kind of what you would find in Conquest and WebCSD. So that's text numeric searching, substructure, reduced cell, and similarity. And the idea is that you would create queries the same way as you would through Conquest. You'd have search criteria that you're looking for. And we'll be covering this in the demo. And on that note, we shall move to the demo. And now I'm going to try to gracefully share my screen in a way that doesn't break anything. And if I find it, this. Now look away whilst I type in my password. Very secure. Right. So this is where I hope you can all see my screen, and I hope it's clear. I've tried to make the font as big as I can without making it ridiculous. So what I'm going to be using here is I've got a text editor. So I'm using VS Code, so Visual Studio Code. I've got a command prompt just so I can show you how you'd sort of run a script. You can use PyCharm, Jupyter Notebooks, or whatever interactive interpreter you want to use. And then I've also got the documentation here just to give a couple of examples of how you would search for things. So the first thing I'm going to do is I'm going to activate my Miniconda installation of the CSD Python API. And just to note, I'm in C drive in the training folder. And the reason I'm in there is because I can have read and write permissions, so I don't have to worry about admin rights. So I'm just going to quickly activate my environment. There we go. And so clear that. So we can tell it's activated because we have this base bracket here. And if you've not used Conda before, that essentially tells you what kind of environment you're in. And so the first thing I want to show you is how you would use the Python API, so how you even access it. So I'm going to be making a reading file. So first thing you want to do is you want to import the IO from the CCDC module. So from CCDC import IO. What this essentially does is just gives you all the reading and writing classes. And we want to do an entry reader. So we want a reader. So we say from IO, get the entry reader. And here you tell the reader, well, okay, where am I reading from? I'm telling it, I'll go to the CSD. That's where I want my entry from. Then I say, I want an entry, and the entry that I want, so from the reader, give me the entry for, let's do paracetamol, 28, my favorite one, for no reason. So what this will do is this will go to the CSD, it will grab that structure, and it will return it to me as an object. And I'm going to put in a couple of print commands just to show you what kind of information you can get out. These are just examples. There's a lot more you can get out of it. So let's say we want the ref code. So I'm using an F string here just because I think outputs look nicer. So identifier. And if I save that, and if I go to my command prompt and I run that, you see here that we get a return. The identifier for that is the ref code, which is what I submitted, which is great. And now you could probably say, oh, maybe you're cheating and you're just returning back that string you've just passed to it. I'm not, because if I ask it for some properties, so let's say the formula and then the calculated density for that entry, if I rerun that, you can see here I get the chemical formula of paracetamol and the calculated density for that. And that's it. That's how you access a structure, essentially in 3 lines of code here, if you like. Now, from the entry, we could go straight to the crystal. So if I wanted to access the crystal, type that in there. All I have to say is, well, crystal, so that's my variable, from entry dot crystal. That's it. And that's how you can get hold of your crystal object. Now, to show you that it is a crystal, I can ask for the cell angles. And if I save that, and run in here, you can see that what I get returned back is a named tuple, which contains the cell angles for paracetamol. And so here we have them stored in their own variables. And just as another example of that, I can access different types of properties. So if I ask for the crystal system and the space group symbol, let's save those. See, it returns back, your system's monoclinic and it's a P21 over N. And just to show you how you'd find this in the documentation, this is what I do. You can scroll down to the bottom and go through the Crystal API things there, or you could search in here. So I'll say Crystal. So this will return every instance where Crystal is found within the documentation. The first one is the one you want to just see what's there. You can see here all the different things you have in it. So you have cell angles, lengths, cell volume, and so on and so forth. Honestly, the list is very, very extensive. And yeah, just wanted to make sure that you were aware that that was there. Just going to make this bigger. Set that up. Right, and then how do we access the molecule? Well, as I mentioned before, the molecule is stored within the crystal or the entry, depending on how you want to access it. For the sake of continuation, I'm going to access it from the crystal. So molecule equals crystal dot molecule, and that's it. So how can you tell it's a molecule? Well, it has atoms. So if I want, let's say, I want to know the number of atoms in here. So number of atoms, and then I say from the molecule, give me the atoms, right? So from this, I should get a number spat out, although it won't be a number because the way it works, what you get back is a list of atoms. So the molecule, so the atoms are stored as a list of objects within the molecule itself. And so that means that, for example, if you then want the number, you just get the list, the length of that list, and that will tell you how many atoms you have in there. The reason for storing it this way will become apparent in a minute, but it does make accessing atoms very easy. So what would you want to know about a molecule? Well, I don't know, is it organic? So is mol organic? So for a molecule, is it organic? And then run that, just clear that. Hey, how about that? Paracetamol is organic. Who knew? There's other flags you can pass to it, so things like is it organometallic? There's loads of, like, yeah, documentations. That's where you find them all. So as I mentioned, the atoms are stored as they're stored in a list. So if I want to have a look at an individual atom, I'll go to molecule and I'll go to atoms again, and I'll just pick the first atom from that list. So that's how you index on a list, if you weren't aware. And then how do I prove it's an atom? Well, very easy, put in the coordinate. This is where I get my typing wrong, because here we go, coordinates. And then if I print that, so I print Python. Hey, we have some coordinates. Now these are Cartesian coordinates. Of course, you can ask for fractional coordinates. And many more. Well, not many more of the types of coordinates, but just many more of the properties. And so here you can see the fractional coordinates are printed underneath. A good couple of features that I particularly really like is occupancy and neighbors. So with these, so I clear that, it tells you the occupancy of the atom, and you can get a list of the neighbors that are bonded to that atom. And I think this is really powerful because you can very quickly start traversing across a molecule just to see how the atoms are connected. And you can also get a list of all the bonds, of course, within a molecule, but I quite like this feature. So I'll just show you that. So as I mentioned before, we have different reading and writing sort of interfaces for the different classes. So that's the entry, the crystal, and the molecule. So you could do what I've just done here, which is read in the entry and then get the crystal, the molecule, and the atoms. Or the other option is you could create a new reader and read in the crystal straight away, for example. So here I'm using a crystal reader, and I'm going to tell it, go to the CSD and get me the crystal. And the crystal that I want from the reader is hexacan. So this will get essentially the exact same structure, but the only difference is it won't contain all the general information. It will contain the crystallographic information we had before. So if I show you what that looks like, you will see that. So I've just basically copied, that was my dog, apologies. I've just copied the exact same things I was looking at before, so cell angles, crystal symmetry, and so on. So if I run that, you see that we're getting the exact same output. So here are cell angles, it's monoclinic, and the space group. And then you can obviously do exactly the same for the molecular reader. I'll just very quickly show you that by just copying and pasting this. And then run that. There we go. So from the molecule reader, from the molecule reader here, I've put it in one line just to save space. You see we still get 20 atoms, and we still get is organic as true, which is great. Now, let's say that you found your favorite structure and you want to save it as a CIF and send it to your best friend because you're really happy about it. So the way you can do that is by using our writing class. Now, for every reading class, we have a writing class as well. So same as before, I'm just going to copy this bit here. So reading in paracetamol, just so we have a structure to work with. And then I'm going to create a file. So I want to give it a file path. Now, I'd always recommend creating an absolute file path just because it saves on confusion as to where your files are after you save them. Relative is fine, but yeah, it's just better practice thing. So because I'm on Windows, I'm using \. If you're on Unix, you're going to be using /. Just keep that in mind. And the R flag is there to stop any double slashes, which you need for Windows. And so the way that we use the writer is the same way as you would write a file in Python in general. So you have to open it and then you have to close it, or you use a with loop. So with io.crystal writer. So here we're using a writer instead of a reader, but we're still using it from the io module. I'll give it a file path to say save this file, and then I'll create it as an object. So crystal writer. So now we're saying is that this here is essentially an instance of this with this file path. So using the crystal writer, I tell it, okay, now, you know what, you know where to go to write the file. What I want you to do is I want you to write this crystal. So, oh, sorry, let me load in a crystal. That would have been awful. Imagine if I did that. There we go. So here I'm basically just grabbing the crystal from the entry, and then I'm saving it here. What I always recommend is that you need to really tell tell your command prompt or whatever you're printing out to what you've just done if you've made a file. So here I've just try and grab into one line. I've basically said print out crystal identifier has been written to, and then the file path. So then I know that that's been done. If I run that, aha, of course this was going to happen. Excuse me for a second. What have I missed out here? Ah, right. So this is when spelling mistakes come in as a problem. So for the crystal writer, the function that you want is write, not writer. Just, yeah, because you're telling it to write. Think of it that way. There we go. So now we have crystal hexagon 28 has been written to this wonderful CIF. Hey, there we go. We have a CIF. Perfect. Now, let's say that the situation is you found a CIF in the wild and you want to open it through the Python API. So we're going to use this CIF as an example. So previously, where we used the crystal reader, so in this case here, we pointed it at the CSD, right? What you could do instead is you could point it at a CIF file or a mol2 or any of the other file types that we support within the Python API. So here, what I've essentially done is I've created an instance of the reader, and I've pointed it at a CIF file. I've told it, hey, look, I'm giving you a CIF. And because the CIF only contains one structure, I only want the first structure in that reader, basically. And so what that will do is that will return the structure that's in the CIF file. And I will prove that to you by adding in these things here. So these are, I'll just make this, can I make this? There we go. Give a bit more space. There we go, much better. So same commands as before, the angle, the system, and the symbol. So if I write those, make sure it's saved. Otherwise, no changes in state. So if I run that again, we can see here for the crystal reading a CIF file, we have the angles, the system, and the space group. Perfect. So we essentially have both done reading and writing for a single file, for a single structure. Right. What about if you don't know what structure you want? You just want to see what's out there. So you want to do a search. So the way that we do, so the search example I'm going to give you today is a very simple text numeric search. So we're going to use from ccdc.search, that's the module that we want. We want to import text numeric search. Now, the way that you use this is you can think about it as you basically instantiate a class that you add queries to. So what I mean by that is we say, okay, we want to do a text search. So we're going to use the text numeric search and we're going to instantiate it there. And I'm interested in looking at a compound with the name aspirin. Okay, right. So for the text search, I'm going to add a query and I'm going to add compound name. And I just add the compound in there. This essentially creates a search query for the CSD. And so I want somewhere to save the results. So I'm going to make a hits variable, and then I'm going to tell the text search to search. That's how you do that. And to see an output, I'm going to write this print statement here, so which basically prints out for this compound, this is the number of hits that you get back. I hope that is clear. What we get, oh, let's save it. See that dot there says I have not saved it. There we go. So now it's going away and it's found 85 hits in the CSD that match up with aspirin as the compound name, which is great. Now, if we wanted to look at these hits and actually open them up, these hits are stored as a list. So we could create a loop. So for hit in hits, and I'm going to look at the first 9. I'm going to put in some print statements here. Now I'm copying and pasting from a previously written thing because I'm sure you don't want to just watch me typing, and also spelling mistakes. So here we're printing out the identifier for that hit. So the hits are stored as entries. And for that crystal, sorry, for that entry and that crystal, we're looking at a space group. And so I hope you can all see what's about to happen is we're about to get the hit list. So here we have the ref code, the space groups for that search. Now, if I added another query to this, what we'd be essentially doing is combining all the queries. So we don't want to do that next. We want to just clear everything. So we do a text search dot clear, and that basically clears out the object so it doesn't have a query stored in it. Now, let's say we want to look across them, like we want to search on a metadata of an experiment. So I want to know all the entries that have a habit of a needle, for example. So I create a search query for a habit with the string as needle. And same as before, do a hits text search dot search. So this goes away and does the searching. And then we want something that returns the results, or that we can see them. So here it just prints out the new list. Clear this. And we should get quite a few more structures. There we go. So it took a little bit longer there, but you can see we got 74,000, well, nearly 75,000 structures. Now, if you do want to combine queries, that's straightforward. You just take your existing object, so that's the text search, and then you just add another query to it. So let's say I want everything that's a needle shape and also has been grown out of water. Right, so this basically just combines the two, and we're going to do the exact same thing over here with water. And what you should get saved is you'll get 75,000 that are needle shaped, and then 1,000 that's needle shaped with water. And that's basically it. That's how you can run a very simple text numeric search. Hope that has been clear and helpful. And with that, I finished the demo.